Great. Okay, folks. So, evening of fun. I'm going to take off my headphones because I don't need to hear anything at this point. And what we're going to do is we're going to answer questions afterwards in Remo. We haven't got it set up to answer questions any other way. I know that Jens was talking about in future he's going to run sessions with 30-minute talks. This is not a 30-minute talk, but it should be reasonably entertaining. It's that time of night. I've tried to make sure that I'm not giving you too many angle brackets and colons and everything. And I thought it'd be an opportunity to put together some things that I've been looking at. Recently in the last couple of years, I've quite got interested in lambdas, not like as in just C++ lambdas, but the original lambda calculus and the influence that it's had on programming languages. Now, tonight we're going to be focusing on C++, and I don't want to just focus on the kind of like the happy day stuff. I want to focus on the weird stuff. So I'm going to tell you immediately, this stuff is not safe for work. I'm not offering you tonight things that you should go and put into production tomorrow. That is not the goal at all. I'm offering you things that are thought-provoking, possibly a little bit mind-bending, a little bit like, oh my goodness, but not really intended for practical use. When I talked about one of these techniques earlier in the year, I had a lot of comments from very serious and earnest C++ers going like, yes, but Kevlin, have you thought about the memory implications of this? I mean, I don't think this is a good replacement for the standard. You need to recognize humor when it comes at you. So with such a ridiculous talk title, I'm trying to make that very clear to you. So lambdas to the slaughter, that's what we're going to talk about. A bit about me. Jens mentioned I've been doing this C++ thing for quite a while. I've got re-involved in the UK C++ panel. I was on that quite a lot in the late 90s and early 2000s. I've been working with the language for about 30 years, on and off, and as it were, the rebirth of C++, C++ 11 onwards, has seen a growth of interest and a huge number of features, not all of which I'm going to say are great, but that's always the case with any language. But it's kind of rekindled my interest. So my background, very much the code face, but also kind of the design thinking, the bigger picture. Co-authored these books with Frank Bushman and Doug Schmidt on patterns, on the code stuff in general. Edited this book 10 years ago, 97 Things Every Programmer Should Know. And in a change from our C++ programming, what I did this year during lockdown, actually, Trisha G and I finished the 97 Things Every Java Programmer Should Know book, which happens to have been finished under lockdown and also published under lockdown. Now, there may be a question, is there going to be a C++ one? This is something that Peter Sommerlad was investigating, but it looks like there might not be an outlet for that, which is a shame. But given that we're on the subject of Java, let's talk about lambdas in programming languages. So when did Java get its lambdas? Well, it got its lambdas in 2014 with Java 8. C++ beat it to it by 3 years. On the other hand, we shouldn't get too cocky. C# had lambda constructs in 2005. The thing it calls lambdas came out in C# 3 in 2007, but anonymous delegates are equivalent to what we're interested in here. JavaScript 95, arrow functions appeared later in ECMAScript 6, but the idea of being able to pass around an anonymous function freely as if it were data, that's 1995 for JavaScript. Now, when we go back a bit further, it's a bit further. We kind of lost out somewhere in a lot of our mainstream languages. Algol 68 had them, anonymous procedures. You could just pass around a block of code, pass around an expression and have it evaluated. The clue there is the year, 1968. But again, before people start saying, well, this is a procedural thing, it's just to point out that it's not just a functional thing. We'll come back to the object thing in a moment. Lisp was the first language to do anything with this. Now, the 1958 that I put there is the year of design. Lisp wasn't fully implemented till 1960. But then again, Algol 68 wasn't fully implemented until the 70s, so I'm not too worried about that. But lambdas, they go back to 1932. That's when Alonzo Church first developed them. They were first described in this paper a set of postulates for the foundation of logic, which is about as readable as it sounds. And then in 1936, a more important paper, An Unsolvable Problem of Elementary Number Theory, basically promoted lambdas. So basically, we've been getting very excited in the mainstream programming languages over the last few years about having a feature that was developed in the 1930s added. I'm kind of wondering what's going to be next. What is it that the 1920s and 1900s have in store for us? But let's have a look at a little bit about the mechanics, and then look at one of the ways in which we can start messing about with it. In fact, I'm going to look at 3 ways this evening. It was interesting. I did a broader talk a while back that where I thought I'd dig up and see what other languages had to say about this. I have an interest in different programming languages, and I found this one in Ruby. Despite the fancy name, a lambda is just a function, peculiarly without a name, which clearly solves one of the major problems of software development, which is, of course, naming. Now, C++ has kind of gone with the minimalist, fairly minimalist approach. Some languages like to call their lambdas lambda, Lambda. We can see that in Python. And we can see that in Lisp, and some of them have a descriptive notation. C++ has decided, since C++ 11, it's going to use square brackets wherever it can to introduce new features. And here we introduce a capture clause, which is kind of related to doing things by closure, but not quite. And it also gives rise to the rather exciting syntax that this is now a syntactically well-formed piece of C++. It is a lambda that does nothing, takes it takes nothing and does nothing and returns nothing, and when you execute it, it does nothing. In fact, you can go as far as this. Shafik Yagmor had this brilliant one on his Twitter feed a while back. This is legal C++. So if anybody ever tells you that C++ is unreadable, don't disagree with them. Just show them this. Just it's an interesting one. So yeah, we can abuse lambdas in some very serious ways. But what do we mean by the core ideas? Because it turns out that unlike some languages that have features called lambdas, funnily enough, C#'s lambdas and Java's lambdas aren't actually, they're not actually lambdas. C++'s lambdas are lambdas. And to understand why, we need to understand kind of the 3 laws of the lambda. So I've got a lambda expression on the screen. In the original lambda calculus, there are no types. It is untyped. What we mean by that is not what we mean by dynamically typed these days. Literally, there are no types. There are only lambdas. There's no other construct. There's no integers. There's no concept of integers. There are no bits. There are no bytes. There are no real numbers. So things we can do. You must be able to define variables. And they can be bound or free variables. You must be able to define an abstraction, a functional abstraction. That's what the concept of the lambda is, with respect to a variable, that is its parameter. And you must be able to apply a lambda to another value, which will in this case be a lambda. So these 3 laws, we actually see if we look at C++, that even in the typed concept, we certainly have it, but it actually works in a relatively untyped way as well. We have these 3 qualities. So yeah, we have those, but not all languages have them. But before we get too attached now, let me just put one thing. I've been writing a bunch of stuff in lambdas recently. I've really got tired of everything having return and everything having to have a closing semicolon. And although it would be nice to have an expression just associated with a function, that's not going to happen for a number of syntactic reasons. I'm really, really kind of hoping that someday somebody looks back at Algol 68 and says, wouldn't it be really cool if the last statement, this is related to an extension that's existed in GCC for decades. Wouldn't it be really cool if we just had the last expression, not statement, actually be the result? That would make our life so much easier. Anyway, that's my wish list item for this evening. Christmas is coming, so if anybody wants to kind of make that proposal, that's great. So they're functions, but actually, if we start looking around in Ruby, lambdas in Ruby are also objects, just like everything else, because Ruby is a uniformly object-oriented language. So that's great. I'm not going to say that in C++ they are objects like everything else, but they are objects. This is an important point. This is how the language extension was made in such a simple way. They are simply anonymous function objects. You write this, compiler generates something along these lines. So you're not actually requiring any clever new concepts of the compiler, the link, or anything like that. It's not really a new language construct in that sense. It's an act of transpilation. But in that sense, we can actually easily render it as something we could have already written, but we recognize the convenience of it. That's its dominant factor. But the point there is that it is already something for which most of the stuff was available in the language. Function call operator being the most obvious one, and then progressively we've allowed more and more deduction to take place. So they're function objects. But let's be absolutely clear. One of the things that we've got to get over this. I saw it on a list the other day when somebody said, "Oh, I've got this functor in C++." That term has a particular meaning. It has a particular meaning in linguistics, where it refers to function words in contrast to content words. So, for example, in this sentence, the word "in" is a function word. It doesn't describe a thing in the world. It's not about content. It just describes a relationship, whereas C++ is a content word. Lambda is a content word. R is not a content word in this particular case because of its linguistic role. Functors, that's the linguistic side. And they also have a special place in category theory. Now, a lot more people know category theory these days because of Haskell and functional programming. But back in the early 90s, Jim Kaplan coined this term functors for objects that could behave like functions or appear to be functions in certain contexts. Honestly, until generic programming really became a thing, until templates actually got supported, function call syntax wasn't actually that useful. It didn't offer you any great advantages. It was a mild piece of syntax sugaring. But in spite of that discontinuity from the early ideas, the pre-template ideas versus those in templates, the term has kind of stuck. And now Alex Stepanov, who is actually a mathematician by training, he did actually pay attention to the language, and he chose the term function object. I used to call them functors, but that's because I didn't know any better, and I'm not a mathematician. But I would urge you to stop using this term. It does have a very specific meaning in category theory that is not the meaning that function object suggests. So we need to look at an example. So we've already messed about with the syntax, but let's really mess about. So how do we explore lambdas? Well, we're going to do this with Fizzbuzz, because of course. And for those of you unaware of Fizzbuzz, Fizzbuzz is a drinking game. It's also an interview question. It's a counting game. And here you go: 1, 2, fizz, any number divisible by 3 is replaced by fizz. 4, buzz, anything divisible by 5, replaced by buzz. Let's see, fizz, 7, 8, and if I say 9, then I get that wrong because it should be fizz and I should have a drink. That's how it works. When you get to something that's divisible by both 3 and 5, so 13, 14, Fizzbuzz. Divisible by 3 and 5, 15, it's replaced by Fizzbuzz. So it's not the world's hardest programming problem, but it is a fun thing to kick around and see what you can do. So here's a fairly regular way of doing this. And I'm going to drop the std : stuff because it really just takes up slide space. It's not really worth doing. String is stood string. There are no other strings. So what I'm doing here is a fairly conventional approach. It's a cumulative approach. In other words, it's a stateful approach. Result is the accumulator. And what I'm doing is I've got various guards that add to, and I've kind of got a construction pipeline there. Okay, I'm accumulating the state, and then I'm making a final check. If there's nothing there, then actually I'm going to rebind that to a conversion. And what comes out of this is I never actually have to say Fizzbuzz, which is kind of cool. It falls out of the flow. But this is very control flow and state oriented. So Maciej Pirog, a few years back, explored an idea in Haskell that was really quite crazy. He's got a talk and there's also a paper. The talk is, the slides for the talk are probably more direct in solving this. The paper is a little more mind-blowing. But he makes the observation: the default action is executed only if some previous actions were not executed. Let's go back. See that? There's the default action. I'm going to take the string. I'm going to take the string form of the integer. That's the default action. And there is a guard. And it only gets executed if nothing else happened. Okay. So yeah, good observation. Now we could get a little bit crazy and say, well, hang on, maybe we can get around this. Maybe we don't need all of that control flow. And it's like, okay, fine, let's try this. And so what we end up doing is crazy stuff like this. I'm going to use a lookup technique. I'm going to use whether or not something is a modulo is divisible by 3 or 5. I'm going to use the result of that as a truth, and Booleans are convertible to ints, so therefore I can use them as array indexes, which is great. And I can just use an array, and I've got my strings there, empty and fizz, so I can concatenate those, and so that immediately looks like I'm doing something really cool. You may notice there is no control flow logic at all in the initialization of result. But, and this is the problem, I still have to have control flow on the next line. I still have to check what was result. Was it empty or not? I still have to make that decision. So I've eliminated all control flow by using lookup, except for that default action. It's exactly as Maciej says in his paper. But there's another point here. This prevents me, if you wanted to do this all in one expression, it's this second check that prevents you doing it as a single expression. Otherwise, we'd be able to somehow fold all of this into something here in the return statement. But unfortunately, that's not possible. So this is we can say, well, hang on, what if we can do this without checking the conditions of the previous actions twice? You might think, oh, no, Kevlin, you're making this too complex. There's another solution here. What about this one? This is actually the more functional solution, because here there is no state change. There is no accumulation of state. Our if statement determines only mutually exclusive options. There's no branching back into the main flow. So I could replace this. I could easily write this as a single expression using the ternary operator, but to save your eyes, I'm not going to do that. So the point there is that this is a purely functional solution. And we may say, look, we've achieved it. Here we are, else, and we didn't have to check any of the conditions kind of twice. Yeah, that's not actually true. We need to understand this. We have checked the divisibility by 3 and 5. That's already been checked. So as it were, we have checked everything twice. We've had to check again. Now, our goal here, can we make the control flow follow the information flow without losing modularity? And the answer is yes. And this is where we slaughter those lambdas. So this is how we're going to do it. We have to watch this one carefully. This is the goal. What we're going to do here is we're going to set up a thing called fizz, a thing called buzz, and a thing called ID. To string is stood to string. N is the argument to the function. So those are all clear. And what we're going to do is ID, buzz, and fizz are all lambdas. They are all function objects. This is a composition. I'm going to pass ID into buzz, which is going to be passed into fizz. And then against that, we're going to execute the string form against the string conversion of n. So what we're going to end up is creating a kind of an onion ring type pipeline with a string form of n. So if I pass in 2, then 2 should go all the way through and come out the other side. If I pass in 3, I pass in 3, and it should go through, but then get replaced by fizz. If I pass in 5 or 10, I should get buzz. And if I pass in 15, 30, 45, and so on, I should get fizzbuzz out the other end. So ID is the easy one. That's the identity operation. You receive a value, you return a value. That's it. Now it gets a bit more interesting. I managed to. I've revisited this one over the years. I'm trying to remember when I first did it. It might have. I don't think I had a C++ 17 compiler when I first did it, although I think it was 2017. And progressively over the years, I've been able to make this more and more auto-based. But there is one bit that we can't get rid of, which is we do actually have to say something at one point about a type, either here or in the return. But that's fine. And that type is going to be, what we're doing is we're passing around things which are functions or function objects that take strings and return strings. That's what we're doing. We are composing with these. What is fizz? Fizz is when you call it, if n is divisible by 3, then we return a function object that will concatenate fizz with whatever f is against an empty string. Otherwise, we will simply return whatever we've just been given. Same story for buzz. And that is how you do Fizzbuzz, with no repeated conditions, no checking of the default, and with lambdas, and in a way that your colleagues will not thank you for, which is an important observation here. This is Anderson's law. I've yet to see any problem, however complicated, which when you looked at it in the right way did not become still more complicated. But I offer it to you as a challenge. If somebody gives you that as an interview question, write Fizzbuzz in C++, do it that way. And by the way, it's quite fun to explore in other languages. Some are harder than others. C++ is kind of in the middle territory. I think Python was probably one of the easier ones. Java and C# needed quite a bit of kicking of the compiler and the types to get it working, although the syntax of use was very light. There was a lot of type machinery that you had to put in. Groovy is quite simple, and so on and so on. So there's a lot of fun to be had with this example and a lot of learning if you can follow it. So that reminder, this is not safe for work. Do this at home, but do not do this at work. So let's talk about something else. Let's talk about something deep, the answer to life, the universe, and everything. Or to be precise, an observation made in Hitchhiker's Guide to the Galaxy. Ford Prefect says, "Oh God," muttered Ford, slumped against a bulkhead, and started to count to 10. He was desperately worried that one day sentient life forms would forget how to do this. Only by counting could humans demonstrate their independence of computers. So let's go back to that second paper by Alonzo Church. What he was exploring was something related to the halting problem and computability and all the rest of it. That need not concern us here. What is interesting is the title of the paper, An Unsolvable Problem of Elementary Number Theory. The interesting thing here is he didn't actually use numbers. There was too much, if you like, he wanted to really simplify things down. So he actually started from nothing. I mean, lambda calculus does not actually have numbers. He basically threw away numbers. There are no numbers in pure lambda calculus. So he invented his own. I mean, that's a very kind of C++ kind of culture, thing to do. Well, we could reuse what somebody else has done, or we could invent it for ourselves and we can build it from scratch. I know, let's build it from scratch. Let's do it ourselves. And that's pretty much what happened. And it's kind of cool. What he basically said is that 0, and he did this in a way that is slightly different to kind of like Frege and Pino's approach to defining the integers. Rather than thinking of these in terms of sets, what he did was he thought of numbers in terms of action or application. So it's not immediately obvious what's going on here. So 0, we're going to treat as an abbreviation of lambda f with lambda x yields x. We're getting a little bit here. 1 is lambda f of lambda x, f of x. We apply the f that we receive as a parameter to x that we receive as a parameter. Okay, still not entirely clear what's going on, but starts becoming clearer when we look at 2. Count the f's. Quite literally, the numbers are count the f's. Or to be precise, the number of times I have applied something. It is the applicativeness of this. So in other words, 3 is 3ness. It is applying something. It's applying a function 3 times. In other words, we are describing by doing. We're not describing by sets. We are describing by doing. So 3 is 3ness. 4 is the 4ness of something, the repetition of something. Now, there's a couple of things we can do to make life a little bit easier. There's one small one, which is worth pointing out. The original lambda calculus, actually a lambda only takes a single parameter. But as a shorthand, given that we often pass 2, then this is the form there. That's something that only a few programming languages have a concept for. Haskell is an example of such. There is a big difference between a function that takes 2 arguments and a function that takes 1 argument in C++. And a function that takes 2 arguments past only 1 argument is what we call a compilation error. So there's no kind of like halfway house and currying or anything like that. But this is a more convenient form. Now, there's a number of other ways we can write this. We can make the 2-ness, 3-ness, and 4-ness more visible and apply it to F all the way down the line. So there's a lot of different conveniences here. As another way of doing this, let's just start with 0. 0 is the not applying of F to X. Then 1 is the successor to 0. So we need to figure out what successor is, but don't worry about it just yet. If I define something or abbreviate something that will give me that, then 1 is the successor of 0. That's kind of logical. Once you have a successor relationship, you can keep on going. 2 is the successor of 0, and so on and so on. And you can do the same trick, or you can just say, wait a minute, why am I even doing this? 1 is the successor of 0, 2 is the successor of 1, 3 is the successor. Brilliant. We just reinvented integers. This is how you do it. So next time, this is kind of like pure software craft movement. Don't trust anybody else's integers. Roll your own. You can create your whole arithmetic system. This is how you write the suck function. This is how you do the successor. Okay. So that once we've got that, we can do all the rest. So that is what that looks like in C++. And now, thanks to the ability to put auto in even more places, we can actually do this in a way that is fully generic and relatively light on the eye. I have formatted this so that you can actually see it. Putting it all on one line really is not helping anybody. So we've got a successor relationship. Great. So we've also got the definition of 0. Again, notice it is, and I've broken this right down to the pure lambda form. I'm not taking 2 parameters. I am taking 1 and then returning something that also takes 1. What are we returning for 0? We're just returning X. We are not applying F, or rather, we are applying F 0 times. Hence, it is 0. So now we know what 0 is. We don't need to talk about it because now we can just define everything else in terms of that, which is kind of cool. Which is great. What we've just done here is, this is a system, this is known as a church encoding after Alonzo Church. It's a church encoding, and these are church numerals. We can do some other things with them. This is kind of an interesting one. So what I'm going to do here is show you the 0-ness or the 1-ness or the 2-ness or the 3-ness of these numbers. That idea that they are effectively, what we've just done is we've associated numbers with iteration. I've also introduced a color distinction here. I also realize that as somebody who's slightly colorblind, I'm not entirely sure what color I'm showing. It could be yellow, but it could be green. I have a sneaking suspicion it's green, but it's not white and it's not black. The only other colors in play on the screen. So what we're going to do here is we're going to, here's a simple function. It's a lambda, which we have given the name +1. We are abbreviating this here. By the way, you'll notice occasionally I'm being very careful about abbreviating. There's no way to define a named function in lambda calculus. All names, except for those of parameters, those are variables. All other names are just abbreviations. What this means is that because the names are not actually definitions, you cannot use them inside the function that's being defined. In other words, the one thing you can't do in lambda calculus is the one thing that everybody associates with functional programming. And everybody associates lambda calculus, somewhat incorrectly, with functional programming. Lambda calculus is the basis of many different paradigms, can be found present in those. As we've just discovered, objects, for example. That means that you can't do recursion in lambda calculus, which comes as a surprise to many people, but it's just a subtle distinction I thought I'd draw out there. Now, the reason I've got a different color here is what I am doing is I'm borrowing from outside pure lambda calculus. So all the stuff in white is the C++ interpretation of pure lambda calculus. I'm borrowing from outside lambda calculus. I'm going to bring in integers, or at least I'm going to bring in something that understands +1 operation. So I'm borrowing that in from another type system, the type system of C++. This is how most people use lambdas. They informally type them or formally type them. So this makes perfect sense. Okay, that's great. So what do we got? We got 0. Okay. Now, what I'm going to do, remember that 0 is the act of not doing something, or rather doing something 0 times. I'm going to pass in a function that is not a pure lambda. It's got something else in it. It's got this ability to add integers. Okay, so I'm going to pass that in. Now, that's not going to do anything. I need to apply it to something. What am I going to apply it to? Well, I'm going to pass in something else from the outside world. I'm going to pass in the real 0, or as real as an int in C++ is. So I'm going to say, I'm going to do +1, and I want +1 to be applied to 0 times, which seems a little pointless, but unsurprisingly, it gives us the answer 0. Now I'm going to pass in +1 to 1, and remember, or _1. Remember, _1 represents oneness. So what I'm expecting is exactly what we get. We apply +1 to 0, and it does it once. And now it gets more interesting, because as we start doing this, what we're doing is we have simply said, hey, you're a lambda, you're an abbreviation, you're a set of lambdas, and I'm going to give you something to chew on. I want you to apply this and something else. Express the concept that you are, which in the case of 3 is 3ness. And we start off with 0, and we apply the +1, and we apply 3ness to it, and we get 3. This is great. We've just reinvented counting. Now we can get a bit more fun. So I'm going to borrow in from Boost here. What I'm going to do is I'm going to take the number 1, and then I'm going to look at the type that we were actually given for n. So if that type was in the previous example, that type would be int. And so therefore, n plus int of 1, well, int of 1 is 1. Okay, that's fine. Yeah, lexical cast will just do this as an identity operation. And we get exactly what we had before. It becomes a lot more fun when we do this, though. If we pass in a string, let's pass in an empty string and then add 1 to it. And in this case, 1, well, becomes stood string, and it's a string of 1. And what we have just done here is reinvented unary counting. Okay, so binary, a lot of people think of binary as being the fundamental counting system of computers, 0s and 1s. The universe only deals with 1s. The universe works in unary, and so we've just reinvented unary here. Again, please do not apply this at work, but it is fun. So we can now also go ahead and define ourselves a square function. So what is square? Well, square is when I give you a number, then you apply it to itself. It's the two-ness of that. Yeah. So it's m squared is I need m applied to m. That's what I need. Okay. So that works quite nicely. The square of 10 with +1 against 0 gives us 100, which is exactly what we're expecting. Now, this idea of church encoding does not just stop with integers. Church encoded the natural numbers, but the idea of church encoding goes much further. We can actually go and have a look at George Boole encoded or codified and formalized propositional calculus in the 19th century, and gave his name to data types everywhere. But it's a very simple value system. It doesn't have all the complexities of natural numbers. You basically got true and you got false, and that's it. Let's do a church encoding for this. What we're going to do is lambda A of B, the difference between true and false is that lambda A of B, we're going to say by convention, true returns the first one, false returns the second. Now, what's interesting about this is actually a little bit like polymorphism. You apply trueness to something, and it will, you apply trueness to two things, and you get the first one, or you get the second one. Or rather, you apply a truth value to two things, and it will either return you the first or the second. This is an if-else, basically. That's what we've just invented here. But we are treating true and false as polymorphic objects. Now, something else that's interesting here. And so, by the way, if you're interested, that's the system that's related to, Smalltalk uses Booleans like this in this sense. We don't tend to use that in most other languages, not even those that normally pride themselves on being object-oriented. What's interesting here is that false if you look at that syntactic form, the names don't matter. The A and the B don't matter. As long as an expression can be reduced, it can be substituted with alternative names and can be shown to be the same, it is considered to be the same. It's what's called alpha equivalent. That's identical to this. So false is exactly the same as this, and we've already seen this. It turns out that false is 0, which is a really interesting coincidence, but we see it in C. You know, the idea of falsehood and 0 are way, way deep. It's not just an arbitrary coincidence. It's a kind of profound thing. In lambda calculus, it's that way as well. And we can do a few other things. We can go ahead and we can encode other data types, a pair. So for that, we're going to need 3 things. And we will return a functional abstraction of those. And if I want to get the second, so P is, if I pass in a pair, then the first is resolved by that expression. The second is resolved by that expression. So I can actually create a church encoding for constructed data types. And then I can extract the values. So in other words, you can do data abstraction with lambdas, which is unexpected. If you look at the first and the second really closely, you will realize that those are true and false. And if we can construct things, when you have 2 things, it turns out that you might say, well, hang on, you can just construct a third and get a tuple and stuff like that. It's like, no, think differently. A pair is all that you need to create a list. You need a value and the rest of the list. A value, and in that holds a value and the rest of the list, and the rest of the list. And before you know it, you've just reinvented Lisp. Now, Lisp uses slightly different vocabulary here. It doesn't say pair, it calls it cons. It doesn't say first or head. It's referred to as car, content address register, and then the tail or the second is content register. And then just so that we can terminate things, we throw in nil, which we've already established. You know, why not? Let's use false. It's being used everywhere else. So we've just gone and reinvented the Lisp, and we've reinvented linked lists and singly linked lists, and of course we've reinvented stacks. We've reinvented the push operation and the top operation and the pop operation, and we will say that stack, I could have called it new, but I'm going to call it stack just so we've got the idea that we are constructing an empty stack. Now, how far can we take this? Yeah, quite a long way. Let's see what it will look like if I did this in C++. A stack of string, not std stack. Stack of string, I'm going to use stackwise terminology. What I mean by stackwise terminology rather than STL terminology. The STL makes everything, offers a uniform naming convention for everything, regardless of its metaphor. It's very useful, offers us uniform access and consistent notation. That's great. But each type normally has some kind of metaphor, which is subtly different. Stacks don't really have a size, they have a depth. Stack is a vertical concept. Queue, if I were to talk about queues, however, queues are not vertical concepts, they are horizontal concepts. Queues don't have depths, they kind of have size, but they normally have lengths because they are horizontal. So in other words, I'm going to use the vocabulary of what stacks are in the real world. So when I create a new one, then the depth is 0. I'm going to make sure, I'm going to avoid any kind of exceptional behavior. I'm going to make this a simple, everything's going to have basically be a full, total function rather than a partial function. So I will, the top operation will return you either a value or null opt, so it's an optional. Then I'm going to push C, and then I'm going to push C++. But notice what I'm doing, I am not inducing any kind of side effect. This is an immutable data structure, and so therefore it's a transformation. What we're doing is we are saying that the push operation does not actually change words. What it does is it returns you the result of having pushed onto that. So that's kind of nice. And then the depth is 2. But we must rebind at every level. So they're always constant operations. The top is C++, and then when I pop, the same works in reverse. So here, pop yields the resulting stack, and the top is C there. And if you wanted to pop an empty one, then it just becomes the identity operation. So it just returns an empty stack. So that all makes kind of sense, which is really nice. What does this look like? Now, there's a lot of different ways of doing this because I've only shown you a syntax of use. And I can do all of this without lambdas. But where's the fun in that? Okay, we're going to make this a little more fun. I can do this with a singly linked list. And in fact, I did that in a C++, C++ users journal article many, many years ago. That kind of equivalent, a singly linked list that had shared representation and held its members as const. So therefore was actually a kind of proper realization in C++ of what a Lisp list would look like, and avoided duplication every time you copied. So you had all these really nice properties and purely functional kind of data structure. We're not doing that clever stuff here. We're going to do other clever stuff. This is our stack. Okay. So stuff you'd expect, a default constructor. Not unsurprising, this is kind of the pair operation or the cons operation. You take the head, you take an existing stack, put them together, now you've got the new stack. So this is how we cons up a list. So you've got an empty one and a way of creating new ones. If you want to create a stack with one element, then I could simply go ahead and construct with the head and an empty stack as the second parameter, and we're good. But we want to use those named operations. So let's use those. Let's see what they look like. What you may not have been expecting is that they look like this. I've decided that I'm going to do all of this with function objects and specifically lambdas. Depth, top, pop, and push are data members, and what they are invocable. So I can use them as if they were functions. That's the syntax you saw on the previous slide. You will notice that there is no representation in the conventional sense of private state. We are going to hold all of the state that we need in the functions themselves. And that's going to be done like this. First of all, we're going to recognize that we don't need any kind of control flow here. An empty stack, its depth is always 0. There's no additional state to return. The top, well, there's never anything there. I never have to do, if the depth is 0, then return null opt, else return whatever the top value is. We know it's empty because we're in the constructor of an empty stack. So it's always null opt. Likewise, pop is always the identity operation. And push, we add the new top and against an empty one. The more interesting behavior is this one. What is the depth? Well, again, it's 1 plus whatever the depth of the tail was. Notice we can see the tail here. We've got a closure over this. So it's 1 plus whatever the depth of the previous thing was. The head is whatever you've just passed in. The tail is whatever you've just passed in other words, the top and the pop. And push is actually pretty much like we had before, but now we've got an additional operation here, and we build on that. So yeah, this is quite good. We take the existing tail, push the head, and then the new top. So that's it. We're done. We've just created this, and we've just done that by constructing from 2 different points. Now, there's a couple of tweaks that I could make here, and then some people don't like to use this kind of like more general open capture. We can be more specific. We can also, for those who care about optimization, but honestly do not care about optimization for this one, we can pre-calculate the actual depth at the point at which it's constructed. And so now what we've got is all of the state has been captured within that set of lambdas. And this leads us to a kind of concluding observation. William Cook wrote this really interesting paper back in 2008, 2009 on understanding data abstraction revisited. And he revisited a paper from the mid-80s that was all about data types, basically types, data abstraction, polymorphism, and there's a lot of really good stuff in that. That is the foundation for many things that we find familiar today. But he revisited that and made this wonderful throwaway remark. Lambda calculus was the first object-oriented language, and because of these polymorphic properties, but also because of these data abstraction properties. So I will close this by making this very simple observation, or rather borrowing. This is all about reuse and looking at the past. I remember that Andrew Koenig, and I don't know if it was on comp.standard.c++ in the 1990s. It was the 1990s, and I think most likely the early 1990s, early to mid-1990s. And he made this wonderful observation that people who brook no compromise in programming languages should program in lambda calculus or machine language. In other words, if you don't believe in compromises, and all programming languages engage in compromise, then you either use ones and zeros or you use lambda calculus, which doesn't even have ones and zeros. You get to craft your own ones and zeros. So normally people talk about, coding at the bottom level, messing about with the ones and zeros. Here we've gone further. We've gone into the substance of the universe. And I hope that has been thought-provoking and interesting. So I will give you a minute or two to gather your thoughts and gather your questions. And I am going to change platform. I'm currently on StreamYard, and I'm going to come over to Remo, and I'm happy to answer questions there. So I will see you in a moment.